Hello, guys. So, in this part of the discussion about rectifiers, we're gonna explore another concept, which is the peak inverse voltage. Okay, the peak inverse voltage is basically the maximum reverse voltage exerted or the diode can see during the off operation or reverse operation in rectifiers. Basically, we see that in our circuits, either the full wave or the half wave rectifier. In some parts of the operation, the diode was reverse, was off, and in some other parts, the diode was forward and on. Okay, so the question is, during this off operation or reverse operation, what was the maximum reverse voltage, the reverse voltage drop on the diode? Okay, so that when we design this circuit, we buy a diode that has breakdown voltage greater than, as a magnitude, of course, than this reverse voltage. Remember that we don't want that diode to break down when it's reverse. In such kind of applications, the rectifier application, whenever the diode is reverse, it should stay reverse and off all the time until it become on again in the forward when it become forward. Okay, and breakdown is not desirable at all. So we must buy a diode with high breakdown voltage, but how much high? Okay, so basically we should calculate the maximum reverse voltage the diode see during operation when it was reverse, when it is reversed. Then we buy a diode with higher than, for example, if the maximum voltage that the diode see is minus 100, so when we buy a diode for such application, minus 101 is good, minus 102 is good, minus 150 is good, minus 1000 is much better. Okay, so let's check that. So we studied 3 circuits, half wave and 2 full wave rectifiers. So we're gonna calculate the peak inverse voltage in each one of these circuits in that recording now. Okay, so let's start by the simplest one, the half wave rectifier. So in the half wave rectifier, to know the peak inverse voltage, just apply or calculate or solve the circuit when it is when the input with its maximum negative voltage. So if this is the input, this is the maximum positive voltage Vmax, and this is the maximum reverse voltage minus Vmax. So calculate the diode voltage when the input is equal to minus Vmax. So we can formulate the problem as follows: find Vd when the input equal to minus Vm. But this is for the positive half wave rectifier, by the way, because the positive half wave rectifier will be reverse in the negative half cycle. In the negative half wave rectifier, it will be positive. It will be reverse when the input is in its positive half cycle. So we must calculate Vd when the input is equal to Vmax, not minus Vmax. So let's calculate this. So the circuit can be reduced to something like this: a resistor or a diode like this, and a battery with voltage equal to minus Vmax. Good. Now reverse the battery terminals and also the battery voltage. So this is R, the diode, and Vmax. And here is positive negative, here is negative positive. We just flipped the direction, so we flip also the value. Okay, and this is basically very reverse. So this is reverse connection. So the diode is off. And the current is equal to 0. So VR equal to 0. Here is VR, here is VD. So let's, from Kirchhoff, let's calculate, the VD. So from Kirchhoff voltage law, Vmax plus VR plus VD equal to 0. Look, guys, all of them are circulated in the same rotation, with the same rotation. All of them is counterclockwise. VR is 0, and Vmax is just a constant. So from this, VD equal to minus Vmax. So this is basically the peak inverse voltage. So the maximum as a magnitude, the maximum voltage the diode can see in reverse, or the peak inverse voltage, is Vmax. Okay, so if Vmax is 100, so we must buy a diode that has peak inverse. That has a breakdown voltage as a magnitude greater than 100. Any value greater than 100. Okay. And let's put this, or highlight this, because we're gonna use it at the end to compare between all of them. Okay, let's do now the center tape full of rectifier. You can choose. So here you have two diodes. You may say I should calculate both. No, because basically the circuit is symmetric. So the peak inverse voltage that you calculate for D1 is basically will be the same if you calculate it for D2. So you can do that as a check. I mean, if you choose to calculate the peak inverse voltage for D1 and it was with some value, okay, let's say minus 100 again, then it should be the same for diode 2. So you can do the same for diode 2 and you should get minus 100. If you get something else, then you have some mistake. Okay, so let's do that. So if this is D1 and this is D2, let's do that for D2. So calculate or find VD2 when V input equal to Vmax. Remember, in the positive half cycle, this is positive, this is negative. So again, here is positive, here is negative. The ground to the positive is negative, the ground to the negative is positive. Okay. So basically here, D2 is reverse because the B is closer to the minimum voltage in the circuit. And D1 is forward because its B is closer to the maximum voltage in the circuit. Okay. So when we apply VM in the positive half cycle, D2 will be reversed. Okay. But D1 is forward in the positive half cycle. Okay. So this happens in the positive half cycle when D2 is reverse. Okay, good. So we have here Vmax at the primary coil. This is 1-to-1 ratio. So we have here Vmax over 2 because this is in the center tape. Okay, so always this point of the ground is the fifth terminal of the transformer, center tape transformer is in the center. Okay, and this is also Vmax over 2. So we need a loop now to apply Kirchhoff and find VD. Okay, so the outer loop or the overall loop is the best one here. So this loop I mean, let's call it 1, and let's have another color. So you have another loop as well. This loop, let's call it 2. So let's write this. We can use either loop 1 or loop 2. Any loop that has D2 is good. So in loop 1, you're gonna use VD1, which is 0.7 at that time when we apply Vmax. Okay, and in VD2, if you use loop 2, you must determine V output when V input is equal to Vmax. Okay, and it will be Vmax over 2 minus 0.7. So if you use loop 1, then we're gonna use VD1, which is 0.7. If we use loop 2, we're gonna need V output, okay, which will be Vmax over 2 minus 0.7. Okay. So that's basically, if you're gonna use, you can use either one of them. So let's go with loop one. So from loop one, so let's see what we have here. So we have a voltage here, Vmax over 2. Another voltage in the same direction, Vmax over 2. Then plus, because this is in the same direction, plus VD1. Then we continue minus VD2 equal to 0. So, oh, sorry, here, VD2 is from negative. This is wrong. I'm very sorry. So let's correct it very quick here. This is negative, this is positive. Okay, and also this is wrong. This is negative, this is positive. Okay. So negative here, positive here, negative here, positive here. Okay. So basically, let's correct that as well. So Vmax over 2, Vmax over 2. Then here, this is opposite. This is in that way. So minus VD1. And let's remove the incorrect thing here. This thing. Okay. And then for VD2, minus VD2 or plus VD2 because it's in the same direction. Okay, plus VD2 equal to 0. That's good. Okay. Again, Vmax that way, Vmax over 2 that way. Then we have here is opposite, then same direction. So we are good. So from that, VD2 is equal to VD1 minus Vmax over 2 minus Vmax over 2 equal to VD1, remember, is 0.7, and Vmax over 2 is just Vmax. Okay, minus Vmax. And you must get something like this because you can check on yourself. If you use the wrong directions that I assumed in the beginning, which is wrong, of course, I just a typo from me, you will find that VD2 is positive, which is wrong because basically it's reverse. Okay, so it must have a negative voltage. Okay, so VD2 is equal to 0.7 minus Vmax. Of course, Vmax is much larger than 0.7. It will be, for example, if we use 1/10, here's the RMS, which is the standard outlet, it will be around minus 155. Okay. So this is basically the peak inverse voltage for the center tape. And we can put, in a rectangle like this and also highlight it because we're going to compare it with other values as well. Good. Now let's do the final one. Of course, you can check by yourself using loop 2. Okay. So let's do it. Let's do that. So let's check here. So this is a check from loop 2. So in loop 2, we have VD2 plus Vmax over 2 plus VO equal to 0. So VD2 is equal to minus Vmax over 2 minus VO, and the VO, remember, is all that thing here, Vmax over 2 minus 0.7. Okay, so this will be minus Vmax plus 0.7, which is the same one that we got from the loop 1. Okay, just a check. So let's do the third one. Full wave rectifier, bridge full wave rectifier. Again, 1-to-1. Okay. So you have here 4, but again, the circuit is symmetric. If you calculate peak inverse voltage for any of them, okay, it's all correct. So you can check by yourself by 4 solutions. You can, for example, calculate peak inverse voltage for D1, then check by D2 or D3 or D4. We have 3 checks. Okay, good. So we have D1 and D2 are reverse in the negative half cycle. So if you want to calculate the peak inverse voltage for the bridge using D1 or D2, you must assume the input is minus Vmax, because you will be reversing the negative half cycle. If you wanna calculate the peak inverse voltage for D3 or D4, you can use the positive half cycle. And at that time, you should find VD3 or VD4 when V input is equal to Vmax. So let's go with the positive half cycle. So find peak inverse voltage for D3, or find VD3 when V input equal to Vmax in the positive half cycle, because D3 will be off at that time. So this is positive, this is negative in the positive half cycle when V input is equal to Vmax. This is 1 to 1. So again, here we have Vmax. This is positive, this is negative. Okay. And as you see here, just a check, D3 is really reverse and D4 is also reverse, because the N is connected to the maximum voltage in the circuit of D4, and the B of D3 is connected to the minimum voltage of the circuit. Good. So this is VD3 in that direction from N to B. Negative here, positive here. Okay. So again, choose any loop and play with it. Okay. We can, for example, go with the inner loop here, this simple loop. Let's draw it with red. This loop here. Let's call it 1. We can go also with another loop, which is that one. So let's do it with green, for example. We can go with this group, with this loop as well. 2. You have many loops here. You have many loops. So you can check by, choose one and check by the others. You have many loops. So let's go by one first. So from loop 1, or let's write that what voltage you're gonna use if you use any of them. So for loop 1, which is the red loop, we're gonna use VD2, and VD2 is basically forward, remember, and when the input is Vmax, VD2 will be forward and on, and they have 0.7. Just to review our when we talked about full loop rectifier analysis, and you will find this what I'm saying. We're gonna also use V output when V input equal to Vmax, and it will be Vmax minus 1.4. Again, review our lecture on the full loop rectifier bridge, and you will find these facts. If we use loop 2, so in loop 2, you have the input here, the secondary voltage, which is Vmax. So Vs is equal to Vmax, because we have 1 to 1. If you have other turns ratio, you should apply the turns ratio. And of course, this will change the peak inverse voltage. You have also D1 in the loop, and D1, remember, is forward in the positive half cycle. So it will be 0.7. So VD1 is 0.7. Okay. So let's do with loop 1. So KVL from loop 1. So this is VD2 direction, and here is VO. So we have VD3 plus VD2 then plus VO equal to 0. All of them are the same direction. Yes. So VD3 is 0.7. I'm sorry, VD3 is our unknown. I'm very sorry for this. VD2 is 0.7 because it's forward and on when V input is equal to Vmax. And the VO is equal to Vmax minus 1.4 equal to 0. So VD3 is equal to minus Vmax, and here is plus 0.7. Okay, plus 0.7. So let's now do the check. So let's check by loop 2. So check from loop 2. From loop 2, we have here Vmax in that direction, or Vs. Then D1 is opposite, so minus VD1. Then VD3 plus VD3, it is in the same direction as the input, equal to 0. Okay, so Vmax and D1 is 0.7 plus VD3 equal to 0. This is basically easier than the loop 1. So from that, or let's do it in another. So from that, VD3 equal to minus Vmax plus 0.7. This is basically the peak inverse voltage. Okay, so let's highlight it. Okay, now let's compare the three together. Okay, so looks like 4. Let's do that with another color. So looks like the peak inverse voltage for the center tape and the bridge are the same, right? Right. Because basically here the turns ratio is 1:1. But again, remember, when the turns ratio is 1:1 in the center tape, the efficiency drops, and the DC was Vmax over bar, not Vmax over bar. And so if you want to increase the efficiency of the center tape and make the DC output, as we see in the last video, 2 Vmax over pi, like the bridge, you will lose two things here. First of all, you will have a bigger transformer because it's 1:2, not 1:1. So you have more turns. And this turn is just something physical, you know, something coil, you know, you increase the coil size. And if you do that and redo your analysis, you will find that the peak inverse voltage will be 0.7 minus 2 Vmax. And that's so you will need now, you know, more expensive diode. Remember, if you find the peak inverse voltage, this is very important observation. If you find the peak inverse voltage out of your analysis here big, that means you need more expensive diodes. For example, let's compare two situations, two circuits. Circuit 1, the peak inverse voltage is minus 100. Circuit 2, the peak inverse voltage is minus 200. Okay, so circuit 2 is worse, or circuit 1, which is minus 100, is better than circuit 2. Let's say why. So circuit 1 has a peak inverse voltage minus 100, circuit 2 minus 200. Because when we're gonna buy a diode, we can buy a diode with breakdown voltages minus 150, minus 170, minus 120, minus 101, minus 102, minus 110, minus 200. Okay. But for circuit 2, which has a peak inverse voltage of minus 200, you must buy diode with breakdown voltage, you know, as a magnitude larger than 200. So you cannot use a diode with breakdown voltage of minus 150 or minus 170 or minus 101. All such, you know, valid diodes for circuit 1 is not valid for circuit 2. So we want always the peak inverse voltage to be, you know, to be low. So basically, you know, the center tape circuit is really bad. But again, this was the evolution, you know, the normal, you know, evolution of the thinking. We start by the half-wave rectifier. If we connect them in that way using center tapes, then we're gonna have a full-wave rectifier, but it's bad. So we go to the, you know, the bridge rectifier. Okay, guys. So again, just to stress on that, it looks like here the peak inverse voltage of both center tape and bridge are the same. Yes, but this is for 1:1. But then you will have another problem with the center tape. Okay. Because the efficiency with 1:1 is half of the bridge. So if you want to increase the efficiency, you're gonna lose the peak inverse voltage. The peak inverse voltage will be 0.7 minus 2 Vmax. Okay. So that's basically, you know, guys, peak inverse voltage. Thank you very much for watching this video, and see you in the next video. Bye-bye.